All right, 12.2, investigating standard deviation. Use technology to find the mean and standard deviation for the data in the dot plots. All right, so let's start off with the partner one. We'll see if we get the partner two, see how long this takes. So I'm gonna make two columns. I'm gonna make one that says X bar, which if you remember is our standard deviation. Is our mean. And then we're gonna use this sigma here, and that represents the standard deviation. Okay, so, all right, so let's get to it. So I'm gonna go to my calculator, I'm gonna go to stat, edit, I'm gonna clear out list one. All right, and I'm gonna plug in every single point on this. Let me see if I can get the brightness to look a little better. Let's see if I turn this off. Sorry, just trying to get the lighting right. Okay, yeah, that looks much better. Now you can see the screen. Okay, so I'm gonna put every point in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 10 numbers. Quickly go to stat, now button right below delete, over to calc, 1var stat, enter. All right, and there I have my mean and my standard deviation. My mean is 5.5. My standard deviation is 2.87. And we'll hold it off at the 100th place. So only 2 decimal places I'm going to say are necessary for this activity. All right, let's do the next one. I'm going to keep that stuff in list one just for fun. And let's do this row now. So now we got 2 values of 10, 2 values of 20, 2 values of 30, 2 values of 40, and 2 values of 50. So we've got a uniform distribution. Do the same 1var stat, but now instead of pressing enter, because then if I did press enter, I would get the exact same stats we got before. So if you don't press anything, it automatically chooses list one. So what I have to do now to make sure, press second, then number 2, see how it says L2 there? Now it's gonna do one variable stat for list 2. We can see now we get a mean of 30, which makes sense, right? This is a symmetrical distribution, and 30 is in the middle, so it must be the mean, with a standard deviation of 14.14. Okay. Next, we are going to look at this one. And you know what? I'm not even going to touch this one, put it in the calculator, and neither should you. What is the mean and standard deviation of this distribution right here? Hopefully, you know the mean is 2. All the points are 2, so there's going to be no difference. It's the only possibility. Standard deviation should be 0, since none of the points ever are different than the mean. It's always exactly the mean, so there's no deviation. There's no difference in any of the values. All right, now I'm going to try and show you a couple of interesting things we can do in this calculator. So the next thing they want you to do is to create a list of 10 numbers with a standard deviation equal to the standard deviation of your first dot plot with a mean of 6. So we're talking about this one up here. So instead of having a mean of 5.5, they want the mean to be 6. They do not want the standard deviation to change at all. It should be equal. So basically what they're saying is, I don't want the shape of the distribution to change, but I do want the values to increase slightly. If we have a mean of 5.5, I really want there to be a mean of 6. So what I can do here is, if I want to bump this mean up half, right? It's at 5.5, it's got to be at 6. I want to add 1/2 to every single value in the data set. Because if I shift it all up by a half, the spacing between the dots doesn't change. If the spacing between the dots doesn't change, the standard deviation will not change either. So I'm going to try this out. Actually, I'm not sure if this will work. I think it will. I think what I can do is, if I go to L3, I can say L3 is equal to list 1 plus 0.5. So what that does is it adds 0.5 to every value in list 1. Let's see if this works. I think it will. And we can see it does. So list 1 and list 3 are exactly 0.5 apart. So let's see if this actually does what I think it's going to do, which is bump up that mean but keep the standard deviation the same. So let me actually double check which list that it was. It was list 3. So let's go to calc, 1var stat for L3. And I can see that my standard deviation is still 2.87 and my mean has jumped up to 6. So as long as you're adding the same number to every single data point, standard deviation is not affected, only the mean is affected. All right, next, 10 numbers with a standard deviation 3 times greater than the data in the first row. So it actually doesn't say anything about the mean being different or the same. All it says is that that standard deviation of 14 has got to be, oh, I'm sorry, we're talking about the first row. That standard deviation of 2.87, we want it to be 3 times greater than that. So I guess that's a little bit less than 9. Okay, so if on our last one, we wanted to increase it by a half, right? So we added 0.5. So what ideas do you have? What could we do to this first distribution? If we want to make the standard deviation 3 times greater, what could I do to my data? All right, well, there's a lot of different ways we could experiment with this. But when I see 3 times greater, I'm thinking maybe I need to multiply my original list by 3. Think about it. Let's just take a look at the numbers in the middle here. 4, 5, and 6, right? They have 1 dot each. If I were to multiply every value by 3, this would become 12, this would become 15, and then this would become 18. There used to be a distance between these two of just 1. By multiplying every value by 3, I've increased the distance between every single point to now be 3. So you'll notice that when you add a number to every point in a data set, it doesn't change the distance because they're all moving up the same amount. When you multiply every number in a data set by the same number, it does increase it. It does increase the mean, but the standard deviation also increases because we're stretching out the spacing between all the numbers. So let's see if that actually works exactly, meaning it's exactly 3 times greater. I'm not sure it's exactly 3 times greater. Let's see. So I'm going to do list 4, and I'm going to make list 4 equal to list 1 times 3. Let's see if that works. So if I look at list 1, I'm at 1. This has 3, 2, 6. So I can see clearly the rule worked. I've actually multiplied every value by 3. Additionally, we can say, oh, in list 1, I go up by 1. And now in list 4, I go up by 3. So that distance between all my numbers has increased by scale of 3. So now let's see if the standard deviation actually went up as well. So that was list 4. So my mean has gone up to 16.5. That's interesting. We should write that down. 16.5. So for this one. Let's see how the standard deviation. And sometimes you'll see it written as standard deviation sub x, meaning it's talking about x is the one variable we're talking about. It's the standard deviation of x. So that's why you see that little x right there. And so this standard deviation is 8.61. Interesting. So that actually did not do what we thought it would. My standard deviation has not, oh, I'm just joking. It did. I keep looking at this second row and thinking, that's not times 3. 8.61, I bet you if I divide it by 3, I'll get pretty close to 2.87. 8.61 divided by 3, and it's exactly 2.87. So it was correct. So if you multiply every number in a data set by 3, the standard deviation will be multiplied by 3. The mean started off at 5.5. Let's see what happens when we multiply 5.5 by 3. That also affects the mean exactly. So multiplying a data set affects the mean and standard deviation. Adding only affects the mean. And I would assume the same is true for subtraction and division. Okay. So let's look quickly here because I want to see if you guys can do this as well. I want you to experiment with the calculator a little bit. So this last row says, come up with 10 different numbers with a standard deviation as close to 2 as you can in 1 minute. So either using Desmos or using this graphing calculator, take 1 minute and try and come up with a data set that has the standard deviation close to 2. Okay, so hopefully you got something close to 2 and you put your final answer in that answer. So I'm going to try and do the same thing. I'm looking at a timer now, and I'm going to try and give myself 1 minute. Go. Okay, so what I'm thinking that I want everything to really be close to this number 2, or at least they should be close to the mean, like about 2 away. So let's say I'm going to put in the middle, I want to put 3 as my middle. So then what's 2 away from 3? Well, that's 1 is 2 away from 3, and 5 is also 2 away from 3. So let's just add a bunch of 1s and 5s in here. Oh, it was a 15. Let me delete that last one. So let's see what we got quick. I still have about 30 seconds before it runs it. My standard deviation is 1.92. Let's see if I can get it a little bit higher. I know what I'll do. Why do I even have 3 in there to begin with? Let's take out that 3, because that's going to be 0 away from the mean. So let's see if this works. Ooh, and I got perfectly on 2 with 10 seconds to spare. All right, so really, as long as you have numbers that are all 2 away from the mean, right? If I have numbers 1 and 5, 3's right in the middle, that's my mean. As long as they're 2 away from that mean, the standard deviation is going to be 2 if you have an equal amount of 1s and 5s in the list, right? I could pick any number. Let's say I want to pick 4 as my mean. Well, I would pick 2 and 6 then. I would just put 2 and 6 and 2 and 6 and 2 and 6 until I've got about 10 values. And I guarantee you that standard deviation is going to be 2 as well. Let's list 2. There we go, standard deviation of 2 also. Okay, so hopefully you're using your calculators or Desmos, because you will definitely need to use a calculator or a computer on your test. All right, that's all for 12.2.